Greetings. We will begin unit 5 today. This is going to be a small unit, just 2 classes today and tomorrow in this unit. The reason is it is based on topics that we have done in a certain sense. It is just a matter of establishing certain connections between the non-relativistic Schrodinger's quantum mechanics and Dirac's quantum mechanics, which we did in unit 3. So, relativistic effects from the point of view of Schrodinger's quantum mechanics can be added as perturbations, whereas from the point of view of Dirac's quantum mechanics they are intrinsic to the very statement of the problem, because that is the very foundation of Dirac's quantum mechanics. So, we will establish some connections between these, and essentially these details are very important because they go to the very heart of spectroscopy and atomic structure, because using spectroscopy you investigate atomic structure, and once you know the atomic structure you can do many other problems, dynamics, collisions and other things. So, essentially you are familiar with the hydrogen atom spectrum. You have a visible part, and an empirical study of this visible part of the spectrum is what led to the understanding of the 1 over n square formula in the Rydberg-Balmer empirical formula, which was later on found in Bohr's old quantum theory and also in Schrodinger's quantum mechanics, which all gave the 1 over n square formula. Now, this structure is a good starting point, but then there is a long way to go, and you keep making these corrections, and as you understand the atomic structure deeper you discover that there is so much more to it than just this 1 over n square. And we already found that the sodium atom does reveal the dependence of energy on the L quantum number, but then there is what was earlier regarded as a hidden degeneracy or an accidental degeneracy in the hydrogen atom, because there was no L dependence of the energy for the hydrogen atom eigenvalues. And we learned that the degeneracy in the hydrogen atom was because of the SO4 symmetry. Okay. Now, let us ask this question, that when you take the relativistic energy, and we have done this in unit 3. So, you remember the Dirac solution to the energy, and Dirac solution has energy which depends not just on the principal quantum number n, but also on the total angular momentum quantum number j. Okay. So, E depends on both n and j, and the degeneracy is 2 into 2j plus 1 fold whenever n is not equal to the kappa quantum number. You remember the kappa quantum number in Dirac's theory, whereas when n is equal to kappa the degeneracy is 2j plus 1 fold. Okay. Now, this is a rather interesting observation, and one would ask the question that does the relativistic hydrogen atom, what is the symmetry of the relativistic hydrogen atom? Does it have SO4 symmetry? And this is a problem of much interest, and in fact it is not very many years ago, in 2008, just around 3 to 4 years ago, that there are 2 very interesting papers by Chen, Deng and Hu, followed up by a comment by Stahlhofen, in which this question was addressed. And you might want to read up these papers, this is, it is always nice to read some original literature, and these questions on whether or not the relativistic hydrogen atom have SO4 symmetry is addressed in these papers. And it turns out that the conclusion of these papers is that the relativistic hydrogen atom does in fact have the SO4 symmetry. But this is a matter of considerable detail, and I will not have the time to address this issue very much in this course, but then we will move on to some of the other relativistic effects. And we learned from the Foldy-Witten transformations, which established the connections with terms which were introduced earlier using perturbative methods in quantum mechanics. So, the terms like the corrections due to the relativistic kinetic energy, or the spin orbit interaction, or the Darwin correction, and so on. So, these corrections, they are not manifest in the Dirac equation. Okay, they are all there, but they are not visible. But when you carry out a series of Foldy-Witten transformations 1, 2 and 3, then you are able to rewrite the Hamiltonian in a form in which these terms become manifest, and in fact they do give what we call as the fine structure of the hydrogen atom, but that is not the end of the story, because beyond the fine structure there is the hyperfine structure because of the electron nucleus interaction. So, beginning with the Balmer-Rydberg formula, you go through a progression of corrections and you develop deeper insight into the structure of the hydrogen atom, which is the simplest atom, but that itself has so much, there is a wealth of physics, there is a wealth of knowledge about quantum mechanics which is contained in the quantum mechanics of the hydrogen atom itself. So, the Schrodinger eigenvalues depend only on n, Dirac eigenvalues depend on n and j, and then there is a further spin orbit splitting, which we have seen, we have discussed this in the context of the Foldy-Witten transformations. The lamp shift causes a dip of the 2p 1/2 level relative to the 2s 1/2 level, and then there is a further hyperfine structure which comes from the interaction between the electron spin and the proton spin, the nuclear spin. Okay. So, because the proton also has got a spin half, the proton spin and the electron spin couple to give you a singlet state and a triplet state between these two, and then these were observed first by Albert Michelson. In fact, before this hyperfine structure he observed in 1881, this was before the famous Michelson-Morley experiment which was done in 1887, and in fact this was one of the major reasons that Michelson got the Nobel Prize. Now, these are the details that one gets into in the quantum mechanics of the hydrogen atom, and if you look at these different corrections, like the relativistic kinetic energy correction, the spin orbit correction, or the Darwin correction, the hyperfine correction, hyperfine structure correction, and so on, all of these are inbuilt into the system. The hydrogen atom, when it exists, it has got all of these interactions. These are not interactions that you can switch on and off from outside. Okay. What you can switch on and off are other perturbations that you can impose from outside, like if you put a hydrogen atom in a magnetic field, you can switch off the magnetic field, you can change its strength, you can change its direction. So, all of these external perturbations are under your control, but these internal interactions like the Darwin correction or the correction due to the relativistic kinetic energy, that is something that you have no control on. That is important even for an electron at when the hydrogen atom is at rest. It does not require the hydrogen atom to be moving at relativistic speeds. It comes from the essentially from the fact that the speed of light is finite, and therefore all the consequences of the special theory of relativity have to be automatically accommodated in this scheme. So, these are internal to the electron proton system. These can be viewed as perturbations, not as perturbations which are imposed from the outside, which are switched on or off, but as perturbations over the previous level of approximation. Okay, so, you begin with a certain level of approximation, and to that you add a perturbative correction, and then you can find what the consequences of this perturbation are using perturbation theory, and typically the perturbations are on this non-relativistic hydrogen atom, for which the Hamiltonian, the unperturbed Hamiltonian, is what you have over here. And you can then think of a perturbation no matter where this comes from. It could be internal to the system like the fine structure or the hyperfine structure or the relativistic kinetic energy term or the Darwin term, or it can be some external perturbation because of the electric field or magnetic field as you do in Stark spectroscopy or Siemens spectroscopy, or it could be due to fields like the lamp shift, okay, vacuum fluctuations and so on. So perturbations in general can be either internal or external to the system, and when you are using perturbation theory, it is important that you take into account all the perturbations regardless of these perturbations being internal or external, because they will have a similar role in the structure of the Schrodinger equation with the perturbation, because these come as additive terms to the unperturbed Hamiltonian. And whenever you make these corrections, always you have to be sure that you do not ignore larger corrections like H2 prime, for example. If it is a correction of a certain order and there is an H3 prime which is larger than that, and if you choose to do perturbation theory only with H2 prime but do not include H3 prime which is larger, then it makes no sense. So all perturbations, all corrections must be introduced progressively, so that the most important perturbations, the largest perturbations, are first considered. And furthermore, all perturbations, all corrections which are of comparable strength, like if H2 prime could be an internal perturbation of the same order as H1 prime, but HB prime is also a perturbation of the same order, okay, then it should also be included regardless of it being internal to the system or something which is imposed on the system from outside. So all perturbations of the same order should certainly be considered on an equivalent footing regardless of these perturbations being intrinsic or imposed on the system. So now we need to review a little bit of perturbation theory, because we will ask this question: what is it that a perturbation does to the eigenstates of a system? Okay, just exactly what will a perturbation do? Does it change the eigenvalues? Does it change the eigenfunctions? Does it change both eigenvalues and eigenfunctions? And then typically what a perturbation would do to a bound state part of a system is that it can certainly change the energy levels, okay, whatever is the energy level can change. It can change in one way or it can change in the other way. So the bound state energies can get more strongly bound or less strongly bound, both possibilities are there. You may have degeneracy which can be removed by a perturbation, and that is a very common thing in spectroscopy, okay. So a perturbation removes the degeneracy. It may remove the degeneracy either partially or wholly. Besides, the perturbation can also introduce transitions and change the occupation numbers of the states. So perturbation can have different kinds of consequences on a quantum system, and what we showed in unit 3 was that the terms which come from the Fuldy-Woutyson transformations, if you remember the Fuldy-Woutyson Dirac Hamiltonian which we arrived at after 3 Fuldy-Woutyson transformations, we recognized that there were corrections due to the relativistic kinetic energy term which were applicable for all values of the L quantum number. Then there was the spin orbit correction which was valid for L not equal to 0, when L equal to 0 it is the same. And then there is also the Darwin correction which comes from the electron wave function amplitude at the nucleus because of this Dirac delta function, and therefore it is relevant only for the s orbitals, only when the L is equal to 0. So we only mentioned these results, and in today's class we will discuss these terms in some detail, and notice that all of these corrections, they are of the order of z alpha square. So, look at this one and this one, they are all of the order of z alpha square. So, they are all of comparable strength, and therefore, they must be introduced from a perturbative approach together. Okay. Over here in the Foldy-Wittyson form, they come naturally, they come together from the Dirac equation, but if they are to be considered perturbatively as corrections to the non-relativistic Schrodinger results, then you cannot take one of them, but you must take all of them, because they are all of the same order. So, notice that each of these corrections depends on L. This is the relativistic kinetic energy correction, there is an L here. The Darwin term also depends on L, because for L not equal to 0, this correction is 0. In fact, it is applicable only for L equal to 0, only for the S states, which are the only ones which have got a non-zero amplitude at the center. And then the spin orbit correction also depends on the L quantum number. But when you add up the 3, you sum over all L, and this is a problem which was included in the assignment given to you, that when you add up all of these 3, you get only a J dependence. Okay, this is a very peculiar and a very interesting result. So, now notice that the dependence on L quantum number goes away, and then the question is, what exactly does a perturbation do to good quantum numbers? Okay, what are the good quantum numbers, and how do you choose a basis set when you are doing perturbation theory? So, these are important questions, and I will remind you that the good quantum numbers are those which come from eigenvalues of the operator which operates, which corresponds to a measurement of a certain property of the physical system, as a result of which the system collapses into an eigenstate, and if it remains in that eigenstate when you perform another measurement. So, you stack a set of compatible measurements, and when you get all of them together, you get a complete set of compatible observations, or equivalently a complete set of commuting operators, and the eigenvalues of these complete set of commuting operators are the ones which are giving you the good quantum numbers. So, this is the essential factor that we need to remember in our consideration. So, now from the point of view of non-relativistic Schrodinger mechanics, quantum mechanics, spin as such does not really exist. The non-relativistic Schrodinger equation has no scope to accommodate spin. The only way to do it is on a completely ad hoc basis. When we discussed angular momentum algebra, we did point out that the definition of angular momentum does allow certain values of the J quantum number, which could be either 0, half, 1, 3/2, 2, and so on. So, half integer quantum numbers do have a place in the algebra of angular momentum quantum mechanics. Okay. That does not require any relativistic quantum mechanics. Nevertheless, non-relativistic quantum mechanics does not assign half integer quantum number to the electron spin, because electron spin has no place at all in non-relativistic quantum mechanics. It can be introduced only on an ad hoc basis, and this is how it was introduced perturbatively over the non-relativistic Schrodinger equation. So, when you do that, your good quantum numbers come from these operators, come from the eigenvalues of H, L square, L z. These are the 3 which give you the N, L and ML quantum numbers, right. And then on an ad hoc basis, you plug in an additional property, spin, the way it was done by Uhlenbeck and Gaudsmit, if you wish. Okay. It comes neatly only out of the Dirac equation, only out of relativistic quantum mechanics, but from the point of view of perturbation of a non-relativistic quantum mechanics, it can be introduced on an ad hoc basis. And then these 4 operators H, L square, Lz and Sz will give you the 4 quantum numbers n, L, ml and ms, and you can use these to describe the quantum state of the system. So, now your non-relativistic unperturbed Schrodinger equation H0 psi, H0 is the unperturbed Hamiltonian. Okay. This becomes a 2 component wave function. The wave function itself becomes 2 component wave function because you have introduced spin on an ad hoc basis with an up state and a down state. So, it has got a 2 valued function, and this is now your unperturbed Hamiltonian, and to this you will make perturbative corrections. The 2 components come from the up state and the down state 1 0 and 0 1 if you wish, with whatever coefficients, and the alternative set of quantum numbers that you can use is not just n, L, ml, ms, but also n, L, j, mj. So, now we have to ask the question, which is the appropriate basis set, okay? And this is at the heart of perturbation theory. Okay, once you sort out these issues, one can do perturbation theory systematically. So, let us consider the first order perturbation theory. In the first order perturbation theory, you know that the correction to energy is given by the expectation value of the perturbation Hamiltonian in the unperturbed state. Okay, this is a well known result which comes from perturbation theory. The question that we are addressing is, what do you use for psi 0? Do you use n, L, ml, ms, or do you use n, L, j, mj, and what is it that determines this choice? Okay. So, these are the questions that we are going to discuss today and in tomorrow's class. The perturbations that we are considering are these: H prime, this is the relativistic kinetic energy correction, then we have the Darwin correction, we have the spin orbit correction. These are the corrections that we need to take into account, and they have a formal place based on first principles in Dirac formalism. When you subject it to 3-fold Tyson transformations, you get the terms that you see on the screen. Now, over here, this is coming from an external magnetic field. So, forget about it if you are talking only about perturbations which are intrinsic and internal to the quantum system. Okay. So, you do not have to worry about the terms corresponding to the magnetic vector potential or this field. For the hydrogen atom, you have got central symmetry. So, the curl of E would vanish for spherical symmetry. So, this term also goes. E phi is the Coulomb potential, which is the 1 over r or Ze by r potential. So, that is the one that is responsible for the bound states or even the continuum states of the hydrogen atom. Mc square is just a constant. Without this A, you have got p square over 2m, which will go into the unperturbed Hamiltonian, right. So, the perturbations that you really need to talk about are only these, which are p4, this is the p to the 4 term with a minus sign, mind you, this is the relativistic kinetic energy correction. Then the other 2 perturbations that you have to consider are the spin orbit perturbations, which is the sigma dot L term, the dV by dr sigma dot L, and then the Darwin term. So, these are the 3 perturbative corrections that we need to discuss, right. So, I will refer to them as perturbations. This is the first perturbation, the relativistic kinetic energy term, and then the spin orbit term, which is the sigma dot L, curl of E is 0, and then the Darwin term. So, these are the 3 perturbations which are intrinsic to the quantum system that we will discuss and see what is their consequence on the solutions to the non-relativistic predictions of quantum mechanics, the Schrodinger predictions of quantum mechanics. Okay. So, now in this context, the question that we are addressing is that when you make these corrections, which states do we choose? Do we choose psi 0 to be n, L, ml, ms or n, L, j, mj? And in your earlier course in quantum mechanics, you would have learned how to make this choice, because there is a very simple and fundamental criterion that you must invoke to make this choice. That is the fundamental criterion which must be made before you begin to use perturbation theory. Okay? And what is the choice? This is, I thought it is best to quote Sakurai from his book Modern Quantum Mechanics. He says, remember the cardinal rule, choose unperturbed kets that diagonalize the perturbation. Okay? This is the cardinal rule. This is what you must do. Okay? So, find out which unperturbed kets would diagonalize the perturbation, and then the choice is done. So, this is the fundamental criterion. In fact, Sakurai goes on to say something further, but I will come back to that residual part of his remark a little later. Okay? So, this is, let us take the first correction now. The first correction that we want to consider is the relativistic kinetic energy term, which is p to the 4 term. Okay? Now, this one, p to the 4 is the square of p square. So, let us see what happens to p square, because p square commutes with the orbital angular momentum quantum vector operator, and because it commutes, because L commutes with del square, you already know that this is diagonal in L, ML and MS. Okay? So, now you know how to make your choice. So, your N, L, ML, MS would be an appropriate basis set to go ahead and make use of first order perturbation theory correction to this because of this term. So, let us go ahead and do it. So, let us take the N, L, ML, MS state, plug in the perturbation. Let us not forget the minus sign, it is minus p to the 4. You remember how the minus sign came, it came from the Foldy-Witten transformations, right. So, when you do it systematically, so that was the advantage of doing the Dirac equation and the Foldy-Witten transformations prior to a discussion on this topic. So, you have the minus p to the 4 over this constant, and you find the expectation value of this operator in the state N, L, ML and MS. So, now this is not a very difficult task. So, let us see how to do that. All the constants come out nicely. Here you have got p square over 2m, which is the kinetic energy operator and the square of that. So, you can get that from this En minus v square operator, and then En of course is a constant. So, twice En is also a constant, and all you need to do is to get the expectation values of V, the potential energy, and V square. Okay? So, if you get the expectation value of V and V square, you can solve this problem readily. Now, that is again not a very difficult task, because V is given by this 1 over r minus Z e square by r is the Coulomb potential. This is the E phi term in the Dirac Hamiltonian, right. And then you can find 1 over r, the average value of 1 over r as 1 over n square a, this is the a is the Bohr radius, and you can find the average value of 1 over r square. So, this is just a matter of carrying out the integrations with appropriate radial functions. The angular parts will give you, they are normalized spherical harmonics, so they will contribute just a multiplicative factor of 1, and essentially you have to carry out the radial integrals to get those expectation values, and the non-relativistic radial functions are well known. So, you can, for whichever state you are carrying out this correction, whether it is 1s or 2s or whatever, you can carry out this integration and get the corresponding correction for the relativistic kinetic energy term. Okay? So, working out these integrals is just a matter of mathematical detail, and you will get, for these corrections, for 1 over r you get 1 over n square a, and for the square of v you get 1 over L plus half n cube a square. So, with these corrections you get this correction delta E1, which is given by you put all of these three terms together, add them up, and then you get a net result for the relativistic kinetic energy term, which is given by this. Okay. So, there are some small minor steps which I have jumped over, and essentially you can see that this is how the relativistic kinetic energy term contributes to a change in the energy that you get from the Schrodinger equation. What are the consequences of this correction? So, 2p and 2s, they are degenerate. Okay. That is the consequence of the SO4 symmetry of the hydrogen atom, right. There is no L dependence, but now there is a correction which depends on L. It explicitly depends on L. So, let us see what this correction does to the energy. So, if you put L equal to 0, and I have taken this formula and put L equal to 0 over here. So, you get 3/4 minus 2 divided by half, and if you carry out this simple arithmetic, you have the correction to the 2s state for the L equal to 0 state, which is given by this factor. So, there is a minus sign here, this is minus E2. Okay. This difference, this 3/4 minus of this number, which is 4. Okay. This comes with a negative sign, which is minus 3.25. So, this minus sign and this minus sign will make it plus, and the correction will have the sign of E2, but E2 is intrinsically negative, right, and you are adding that to the non-relativistic energy. What are you adding? You are adding a negative term. So, whatever was already negative will become even more negative, right. So, this is your energy axis, this is the Rydberg series limit, this is the E equal to 0, and therefore, this relativistic kinetic energy correction causes a dip in this value. From here it is lowered by this amount. Okay, this is the result of the relativistic kinetic energy term. This is what it does to the 2s state, but it is different for 2p, right, because for 2p L is equal to 1. So, here the E2 will be the same, but the correction will be different because L is different for the 2p. So, now for 2p you put L equal to 1. So, in the denominator here, instead of L plus half, you have 1 plus half, and this difference is still negative, but it is a rather small number. Okay, this is minus 7 over 12. The previous number which had appeared over there was like minus 3.25, right. So, this is a smaller correction, and therefore, this again, these two minus signs cancel, the correction has the sign of E2, which is intrinsically negative. So, the energy does become more tightly bound as such, but by a smaller amount, by a rather small amount. So, these are the two corrections, and if you now consider both, so 2p has dipped by a small amount, 2s has dipped by a larger amount because of the difference in these two numbers. This is 7 over 12, this is 3.25, right. So, now may I ask if the 2s 2p degeneracy has been removed in the hydrogen atom? Would it be appropriate to say that the hydrogen atom will not have degeneracy with respect to the 2s and 2p states because of the relativistic kinetic energy correction? But then what did we say earlier at the beginning of the class? I showed you some pictures. I showed you the Schrodinger energy levels, then I showed you the Dirac energy levels. Yeah, there are other terms. Okay. So, these are not the only two terms, okay. There are other terms, and then now when you include the other terms which make corrections of the same order of magnitude, then everything will fall in place, and this degeneracy is in fact removed, but only by the lamp shift. Okay. The relativistic kinetic energy term does not really remove this degeneracy, because whatever it does to the energies is compensated for by the corrections in the spin orbit term. Okay. There are other corrections. So, when you add up all the corrections, then you have a different story, and you need to wait to plug in the lamp correction, the lamp shift, to remove this degeneracy. Now, the essential point that which is highlighted over here in today's discussion, there are a couple of points. One, how do you choose the unperturbed states? Okay, what is the fundamental criterion? Because whenever you use perturbation theory, this is the guiding principle for which I quoted Sakurai from his book, and those of you who have read Sakurai would have come across the quote which I mentioned, and perhaps you remember the remaining part of his quotation. Is there anybody who does? It is the remaining part of the quotation. If anybody has read, I can assure that he cannot forget, he or she cannot forget that. So, I will let you think about it. Okay. We are certainly going to come back and discuss the other part of Sakurai's quote, and for today our important lesson is to take into account all corrections which are of the same order of magnitude. If you take only one, you would be led to a wrong conclusion that the relativistic kinetic energy term, in fact if that is the only correction you made, you would go ahead and conclude that 2s and 2p are no more degenerate, and you would expect to see in your observations in the spectrum that you will record, you will expect to see these energies to be at different levels. That of course you do not see, and the reason you do not see is because there are other corrections which are of the same order of magnitude, which you should also take into account. So, there are two major learnings to take home today. One is how to choose the basis set, and second, to make sure that whenever you are doing perturbation theory, all corrections which are of the same order, which are of equal importance in strength, regardless of they being internal to the system or external to the system. In this case, all the three are internal to the system, but we are going to have to remember this even when we go beyond this, because later on we will put this atom in a magnetic field when we discuss the Zeeman effect, okay, or in an electric field when we discuss the Stark effect. The question that will come up is, if you are going to study Zeeman effect using perturbation theory, which is a perturbation of the non-relativistic Schrodinger equation for the hydrogen atom, or some quantum system, whatever, then if you are introducing corrections of a certain order using perturbative methods, have you included other corrections of the same order? Okay. And this will obviously depend on the strength of the magnetic field. If you are doing Zeeman effect, right, for very weak magnetic fields, you may have the perturbation which is more important due to internal interactions, okay. But if you increase the strength of the magnetic field, then the perturbations due to external fields could become more important. And then how you do perturbation theory what is the basis set, and unless you make that choice correctly, you cannot really use perturbation theory. Okay. So, these are the important things. I am going to stop here for today. The 2s 2p degeneracy is not actually removed because of the other corrections, which I will be discussing in tomorrow's class, and today we considered the correction due to the first perturbative correction, which is the relativistic kinetic energy correction. We also have to do the spin orbit interaction correction and the Darwin term. And the question which is going to be raised again is, when you deal with these two perturbations, which will be an appropriate set? Will you use NL-ML-MS or would you use NL-J-MJ? Okay. So, these I will leave you with these questions and stop here for today. If there are any questions, I will be happy to take. No questions. Thank you.